Okay, this is problem number 34 of our related rates problems. We have a walker A and a walker B walking on straight streets that meet at right angles. A approaches the intersection at 2 meters per second, so we'll start to label this. And walker A, we're going to say, is up here. We're going to say the intersection is down here. Maybe we'll call this coordinate Y. We have A approaching the intersection at 2 meters per second. So we could say it's, and that's a rate. It doesn't say it in here, but you can see meters per second is a rate. So we've got dy dt is 2. And since A is approaching the intersection, your y-coordinate is getting smaller. These x and y's are measures of distance. So we call that a negative 2 meters per second. All right, that was walker A. Walker B is over here. B moves away from the intersection, and B's rate is 1 meter per second. So we'll label this x, and we can say dx dt is 1, and that's a positive 1. And that's a positive 1 because your x-coordinate is getting larger. Not so much left or right is involved, but you're walking away from the intersection, so your x distance is getting larger. All right, at what rate is the angle theta? And again, we have to look in the book for the picture, but the angle theta, they kind of complete our triangle here. And let's get a nice line here. They complete our triangle. They draw a line in here for our triangle. And the angle theta, they're talking about kind of line of sight distance from, I guess, from the horizontal walker B looking up at walker A. But that's the angle theta that we're talking about. All right, at what rate is the angle theta changing? So they'd like to know d theta dt, that'll be our question, when A is 10 meters from the intersection. So it would be when y equals 10. A is 10 meters from the intersection. And let's see, B is 20 meters. So when x equals 20. All right, express your answer in degrees per second to the nearest degree. And again, in terms of AP, that should bother you a little bit, that last part of the question, because we know we're going to use radians. And to the nearest degree, they usually want, 3 decimal places. But we'll kind of work with that at the very end. All right. As soon as they bring in an angle, you're thinking of a trig function. And again, you have 3 choices. You have 1 good choice and 2 bad choices here. But we could have the sine of theta. We can have the cosine of theta. And we can have the tangent of theta. When we look at those 3 choices, or 3 options here, we notice here on our left, we've been given information about x and y. We've been given no information here about our hypotenuse. Certainly it's changing. So our hypotenuse, going up and down between A and B, it's changing. We're not sure how it's changing. We're not sure what the length of the hypotenuse is. And so it'd be nice if we could avoid h. So given that fact, we look at our trig functions. We know sine has a hypotenuse in it. We know cosine has a hypotenuse in it. So we would lean, hopefully you would lean towards, let's use the tangent. So what's the tangent of theta? Well, the tangent of theta is the opposite side, which is y, and the adjacent side, which is x. All right, we want the final question is d theta dt right here. So let's take the derivative with respect to time. So I'll take the left side, the derivative with respect to time, and the right side, the derivative with respect to time. Okay, left side, the derivative of the tangent gives me the secant squared of theta. And then don't forget your chain rule, d theta dt. That's very important because d theta dt is our question. And now on the right side, look at that. Y is a variable. X is a variable. We are kind of stuck in this problem. We have to do a quotient rule. And most of the previous problems, we're able to avoid it. And this one, we can't avoid it. So I've got ho d high minus high d ho all over ho squared. And now we are essentially done with this problem. We know what x is. We know what y is. We know dy dt. We know dx dt. The one thing we're still looking for is a secant squared of theta. But we'll come back here and remind ourselves, give ourselves a little more room maybe. Remind ourselves What's the secant? The secant is a reciprocal of the cosine. What's the cosine? It's the adjacent over the hypotenuse. And our adjacent side for this angle is x, and our x is 20. And with the Pythagorean theorem, we can figure out the hypotenuse. We have a 20 squared. We have a 10 squared. So it looks like 400 plus 100. That would equal our hypotenuse squared. So it looks like our hypotenuse is the square root of 500. I know I can simplify that, but I'm just going to leave it as is for the moment because that was the cosine. The secant is reciprocal, and I want the secant squared. So once I square it, I'll get rid of the square root anyway. So I come back up here to my secant squared. I just figured out the cosine. So the secant is reciprocal, so I'll put in the square root of 500 all over 20. And it was a secant squared. Here's d theta dt. And on the right side, I sub in the values I know. What is what is x? X is 20. dy dt, that negative sign is very important. That's a negative 2. What is my y coordinate? It is 10. Dx dt was a positive 1. And it's all over x squared, which is 20 squared. All right, let's do a little math here. I've got 500 over 400. That'd be d theta dt equals, oh, look on the bottom here, another 400. And the top here, it looks like a negative 40 minus 10. Looks like a negative 50. So, doing just a little bit more work here, I can see the 400s cancel out. And it looks like d theta dt, if I divide by 500, it looks like d theta dt is going to be negative 1/10, so negative 50 over 500, or negative 1/10. And those units are radians, radians per, I think we're per second here. Let me just double check the per second part of that. So radians per second. So negative 1/10 radians per second. Personally, I kind of like that answer, and I would be tempted to stay with that answer, negative 1/10 radians per second, except the book wants this in degrees per second to the nearest degree. So we bring out a calculator and maybe have some intuition into this. You know, how big would 1/10 of a radian be? You know, a radian is 57 degrees, so I'm going to guess 1/10 of a radian is 5.7 degrees. If not, we can remember how you convert it. Here's a tenth of a radian, and we know we want, there's 180 degrees per pi radians, so times 180 divided by pi radians. That's our conversion factor. There's 180 degrees per pi radians. And we take that, and no big surprise, I hope, but we get 5.729. And I'd be tempted, oops, don't want that whole thing, just that part. I'd be tempted to keep 3 decimals personally, just in good practice for the AP. We'll give ourselves a little more space here. So I would say d theta dt, it's always okay to give extra decimals, is negative 5.729. You don't have to round in the AP. You could round. Or so if you said negative 5.730, that would also be okay. And those units are degrees per second. So degrees per second. And that completes problem number 34.